All right, let's dive into the world of AI, specifically generative AI. And we're going to be looking at a book called Generative AI with Python and TensorFlow 2. And the authors of this book are Joseph Babcock and Raghav Bali.
This book is like a really great roadmap, I think, for anybody that wants to understand really
Yeah.
how to actually build generative AI models.
Yeah, and I think it's fascinating because a lot of people talk about generative AI now,
Sure.
but most people probably don't really know, like, how it works. And so we're going to be taking a deep dive into each chapter of this book, trying to get a better understanding of this really exciting field. So let's start with chapter 1, an introduction to generative AI, drawing data from models. And this chapter starts off by talking about the difference between discriminative and generative AI.
A discriminative model, you can think of this as like a detective trying to solve a case based on evidence, right? So they're really good at predicting things like, is this email spam? Or not spam, what's the next word in a sentence, that kind of thing. Generative AI is different. It's more like an artist. It doesn't just predict. It actually learns the underlying patterns in data and then uses that knowledge to create something entirely new.
So it's kind of like if you fed a bunch of pictures of cats to a generative AI, it could then create a new picture of a cat that's never been seen before.
Exactly. And it really goes beyond that. This is the technology that's behind those deep fakes that you see online, where somebody's face is being replaced on a video seamlessly. Or even in music. There are AI algorithms out now that can compose entire symphonies that would fool seasoned musicians.
Wow, that's incredible. I've definitely seen examples of deepfakes online. And it is a little bit unnerving, but I'm also really fascinated by it.
Yeah.
And this is all stuff that's happening now. This isn't like some far-off science fiction. This is stuff that's happening in the world today.
Exactly. And chapter 1 covers even more allocations. For example, image generation using models like StyleGAN, which can create photorealistic images of people that don't even exist. Text generation, where you can actually create AI systems that can hold natural conversations over the phone, like Google Duplex. Their sound composition, using algorithms like MuseGAN to synthesize realistic music tracks.
Okay, so chapter 1 really sets the stage for what generative AI is capable of. But I'm guessing this book also gets into the nitty-gritty of how these models are actually built. So let's move on to chapter 2, setting up a TensorFlow lab.
This is where we really get into the tools and the environments that you need to build these models. And primarily, we're going to be using TensorFlow 2.0, which is an open source library developed by Google. And it's become really the industry standard for building and training deep neural networks.
I've heard of TensorFlow before. I know it's used by a lot of different companies and organizations for their AI projects.
You're right. It's very popular.
So what makes it so special?
It's very flexible, it's scalable, it's efficient, and it's very well supported. There's a huge community around it.
Okay, so we've got TensorFlow, but it looks like this chapter also talks about Docker and Kubernetes.
Right. So Docker is a way to create a consistent environment for your projects. It uses what are called containers to package up your code and all of its dependencies. And that way, no matter what kind of computer you're using, whether it's a Mac or Windows or Linux, you can be sure that your project is going to run smoothly.
So it's kind of like shipping your project in a box that has everything it needs to run.
Exactly.
And what about Kubernetes?
Kubernetes is a way to manage complex applications, especially in the cloud. So it kind of makes sure that all the different parts of your project are working together seamlessly.
All right, so we've got our tools set up, we've got our environment ready to go. Now let's get into the real brains of these AI models. Chapter 3, building blocks of deep neural networks.
This chapter really gets into the fundamental concepts behind deep learning, which is at the core of most generative AI models.
I've always been fascinated by the idea of neural networks.
Yeah.
I know they're inspired by the human brain.
Right. The early pioneers in the field looked at how neurons in the brain process information, and they tried to recreate that artificially. So in a neural network, each artificial neuron takes in a set of inputs, performs some simple calculations, and produces an output.
So we're basically building artificial brains.
Well, not quite that sophisticated yet, but the fundamental principles are similar.
Okay, so how do these artificial neurons actually learn and solve problems?
Well, these neurons are connected to each other, forming networks. And by adjusting the strength of these connections, the network can learn to perform different tasks.
So the more neurons we connect, the more powerful the network becomes.
In a way, yes. And by arranging these neurons in layers, we create what's called a multi-layer perceptron. And this allows us to build more complex and sophisticated models.
And one of the key breakthroughs in deep learning, was the development of backpropagation.
Right. Backpropagation is an algorithm that allows the network to learn from its mistakes by adjusting the connections between neurons.
So it's kind of like the network is constantly refining its understanding of the data.
Exactly. And TensorFlow actually makes this process much easier by automating a lot of the complex math involved in backpropagation.
Okay, so we've got neural networks, we've got backpropagation.
Right.
What other building blocks are there in deep learning?
This chapter also talks about convolutional neural networks, or CNNs, and recurrent neural networks, or RNNs.
Okay, what are those?
CNNs are really good at processing image data. They're inspired by the visual cortex in the brain. They use these things called convolutional filters to extract features from images.
So CNNs are kind of like the eyes of the AI.
Exactly.
Okay, and what about RNNs?
RNNs are designed for processing sequential data, like text or music, where the order of the elements is important. They have this kind of memory that allows them to keep track of previous inputs.
So they're kind of like the memory of the AI.
Precisely.
Okay, so we've got our building blocks, we've got our tools, we've got a basic understanding of how these neural networks work. And let's get into some specific applications.
Yep.
Chapter 4, teaching networks to generate digits. This chapter focuses on the MNAS database, which is a classic data set of handwritten digits.
This chapter is really about a groundbreaking discovery that changed the way we think about AI learning. Back in 2006, some researchers found that if you train a network to generate something, like handwritten digits, it could actually improve its ability to recognize those digits.
So you're saying by teaching the network to create something, it became better at identifying it.
Exactly, and this is kind of counterintuitive, but it turns out that understanding how to generate something gives the network a much deeper insight into the patterns that define it.
That's fascinating. And what kind of model did they use to achieve this breakthrough?
They use a model called the Restricted Boltzmann Machine, or RBM.
And what is that?
It's a type of neural network that's inspired by principles of statistical mechanics.
Okay, now we're getting into physics.
Right. So statistical mechanics is a branch of physics that deals with heat and energy and probability. And RBMs use the concept of energy functions to learn the probability distribution of the input data.
So it's kind of like the network is trying to find the most stable configuration that explains the data.
Precisely.
Okay, so we've got RBMs, but how do we actually train them to generate these digits?
We use a technique called contrastive divergence, or CD.
Now, what does that involve?
Oh, it's a bit complex to explain in detail, but essentially it involves adjusting the connections between the neurons and the RBM to minimize the difference between the data generated by the RBM and the actual training data.
So it's kind of like a game of hot and cold, where the network is trying to get closer and closer to generating the right output. And once the RBM has learned to represent the data well, what can we do with it?
Well, we can stack multiple RBMs on top of each other to create a deep belief network, or DBN.
A deep belief network.
Yeah.
What does that do?
This allows us to build more powerful models that can learn more complex features.
So like building a hierarchy of understanding.
Right.
Okay, so we've got RBMs, we've got DBNs, and we've learned how they can generate digits. But what about more complex images, like faces or objects?
That's what we'll talk about in the next chapter. Chapter 5, we're going to explore a more powerful model called the variational autoencoder, or VAE.
Okay, I'm intrigued. Let's dive into that.
VAEs kind of take the idea of an autoencoder to the next level.
Okay.
So an autoencoder, you can think of it as, like if you have a large image and you want to send it over a slow internet connection, you would compress it first, send the compressed version, and then on the other end, you would reconstruct the original image.
So kind of like data zipping and unzipping a file.
Right. But VAEs go a step further. They don't just compress the data. They actually learn a meaningful representation of the data in what's called a latent space.
What is latent space?
Latent space, you can think of it as like a map where similar data points are clustered together.
Okay.
So it's like if you have a messy room, you might put all the books on one shelf, all the clothes in the closet, and all the toys in a bin. And that way everything is organized. And it's easier to find what you're looking for.
So the VAE is kind of organizing the data.
Exactly. And this latent space is what makes VAEs so powerful for generation. Because by sampling points from this organized latent space, we can then decode those points to create entirely new images that resemble the training data, but aren't exact copies.
So it's like VAE is learning the underlying structure of the data and then using that knowledge to create variations.
Exactly.
Okay, so we've got this latent space, we've got this idea of encoding and decoding. But how do we actually train a VAE?
We use a special objective function called the variational lower bound, or ELBO.
LEB?
Yeah.
What is that?
It's a bit technical to explain in detail, but essentially it ensures that the latent space is both informative and well-structured. So you can think of it as, like, if you're an architect designing a building, you want to make sure that the building is both functional and aesthetically pleasing. The ELBO is kind of like the building code that guides you to create a structure that meets both of those requirements.
Okay, so the ELBO is kind of like the rules that the VAE has to follow to make sure that it's learning a good representation of the data.
Exactly.
Okay, and this chapter also mentions something called the reparameterization trick.
Right, so the reparameterization trick is a clever technique that allows us to use backpropagation with VAEs.
Okay, I remember backpropagation from chapter 3.
Right.
So this trick is basically a way to make backpropagation work with VAEs.
Exactly.
Okay, so VAEs sound really cool. They can generate more complex images than RBMs. But can they generate truly realistic high-resolution images like we see with GANs?
That's a great question. And it leads us to chapter 6, image generation with GANs.
Okay, GAN.
GANs, or generative adversarial networks, are really the rock stars of generative AI. They're capable of producing stunningly realistic images that are practically indistinguishable from real photographs.
I've seen those fake faces online that are generated by GANs. And it is mind-blowing how realistic they look.
Right. And what makes GAN so powerful is their unique training process. They consist of two competing networks, a generator and a discriminator. And it's kind of like a constant game of cat and mouse.
Okay.
The generator is trying to create fake images that are as realistic as possible, while the discriminator is trying to spot the fakes.
So they're kind of working against each other.
Exactly. And this adversarial process pushes both networks to improve, leading to incredibly realistic generated images.
That's fascinating. And this chapter goes into detail about different GAN architectures, like the vanilla GAN, DC GANs, GANLs, and WGANs. Can we break those down a little bit?
Sure.
What is the vanilla GAN?
A vanilla GAN is the most basic type of GAN. It uses simple feed-forward neural networks for both the generator and the discriminator.
So it's kind of like the starting point for more complex GAN.
Exactly.
Okay, and then we've got DC GAN.
DC GANs, or deep convolutional GANs. They use convolutional neural networks, or CNNs, which we talked about earlier.
Right.
And they're really good at processing image data, so they're able to generate higher quality images than vanilla GANs.
Okay, so DC GANs are kind of like the next step up.
Right. And DGANs, or conditional GANs, they allow us to generate images based on specific conditions or labels. So, for example, you could train a CGNN to generate images of different breeds of dogs based on a label that specifies the breed.
So it's like giving the GAN some extra information to guide the generation process.
Exactly.
Okay, and then finally we've got WGANs.
WGANs, or Bosterstein GANs, they address one of the big challenges in training GANs, which is instability. They use a different loss function. It leads to more stable and consistent results.
So WGANs are kind of like the more reliable members of the GAN family.
Yeah, you could say that.
Okay, so we've got all these different GAN architectures, but even with all these advancements, GANs still have some limitations, right?
Right. Training GANs can be quite challenging. They can be unstable, and they can sometimes suffer from what's called mode collapse, where the generator gets stuck, generating only a limited variety of images.
So even AI can get stuck in a rut.
Yeah, sometimes.
Okay, but speaking of art, I've seen those apps. That can make your photos look like famous paintings. Is that GANs at work too?
Yes, that's called style transfer. In Chapter 7, style transfer with GANs dives into that world.
Okay, so style transfer is basically taking the style of one image and applying it to another image.
Yeah, exactly.
How does that work?
There are two main approaches: paired style transfer and unpaired style transfer.
What's the difference?
Paired style transfer relies on having paired training data, where each input image has a corresponding target style image. So, for example, you might have a photo of a cat and a painting of a cat. And you would train the network to transform the photo into the style of the painting.
So it's like showing the network
Yeah.
a before and after picture.
Exactly.
Okay, and what about unpaired style transfer?
Unpaired style transfer is even more impressive because it doesn't require those paired examples. So you can just give the network a bunch of photos
Yes.
and a bunch of paintings, and it will learn how to transfer the style from the paintings to the photos.
Wow, that's amazing.
Yeah, it's really cool.
This chapter mentions a specific model called CycleGAN.
Right. CycleGAN is a popular model for unpaired style transfer. It uses 2 generator networks and 2 discriminator networks to transform images back and forth between 2 domains, like photos and paintings.
Okay, so it's a cycle of transformations.
Exactly.
And that helps the network learn how to transfer the style.
Right.
Okay, so we've talked about style transfer, which is really cool.
Yeah.
But it also makes me think about deepfakes again,
Mm-hmm.
because we're talking about deepfakes manipulating images. I know Chapter 8, Deepfakes with Jans, gets into that.
Right. Chapter 8 is all about the world of AI-generated videos that can manipulate faces and create very realistic but fake content.
Deepfakes are both fascinating and unsettling. It's incredible how realistic they could be, but it's also a little bit scary to think about the potential for misuse.
Absolutely.
So this chapter kind of delves into the technical aspects of how deepfakes are created.
Right. It talks about different techniques that are used, like the facial action coding system, or FACS, which is a way to understand facial movements and expressions, 3D morphable models, or 3D which are used to represent and manipulate facial structures, and facial landmarks, which are key points that define facial features.
So it's like breaking down the face
Yeah.
into its individual components and then using those components to create the deepfake.
Exactly.
And this chapter even walks you through a simple face swapping example.
Yes, it shows you how to use a basic autoencoder architecture to swap the faces of 2 different people.
Wow, that's pretty cool.
Yeah, it's a good illustration of the basic concepts.
Okay, so we've got this basic face swapping example, but I'm guessing there are more complex deepfake architectures.
Yes. The chapter goes on to discuss how you can use Pix2Pix-Jans for face reenactment.
Pix2Pix-Jans again?
Right.
They seem to be.
Yeah.
Pretty versatile.
They are.
So how are they used for face reenactment?
In this context, Pix2Pix-Jans can be used to map facial landmarks from a source video onto a target person's face, creating very realistic reenactment.
So it's like you're puppeteering someone's face using AI.
Right.
That's both amazing and a little bit creepy.
Yeah, it definitely raises some ethical concerns.
Yeah, because if you can create these realistic deepfakes, it's hard to know what to believe anymore.
Right, and the chapter emphasizes the need for responsible use of this technology, as well as development of detection methods to combat malicious applications.
It's like a ongoing arms race between the people creating deepfakes and the people trying to detect them.
Exactly.
Okay, so we've explored the visual side of generative AI.
Yeah.
But what about language? Can AI generate human-like text?
It can, and that's what Chapter 9 is all about, the rise of methods for text generation.
Okay, this is something I'm really interested in.
Yeah.
Because I've seen those AI writing assistants that can, like, complete your sentences or even write entire paragraphs.
Yeah.
And it's pretty mind-blowing.
Right, and this chapter starts with the basics of representing textual data in a way that AI can understand.
Okay, so how do we do that?
Well, one approach is the bag of words model, or the word A.
What is that?
It's a very simple approach
Yeah.
where you basically just count the number of times each word appears in a document.
So it's like throwing all the words from a book into a bag and shaking it up. And then you just count how many of each word you have.
Exactly.
All right, that seems pretty limited.
It is. It doesn't really capture the meaning of the text.
Yes.
Or the order of the words. So we need something more sophisticated.
Okay.
And that's where distributed representation methods come in.
What are those?
These methods learn dense vector representations of words that capture their meaning and their relationships to other words.
So it's kind of like creating a map of the language where similar words are clustered together.
Right.
Okay, and this chapter goes into specific methods like word2vec, glove, and fast text.
Right. Those are all popular methods for learning word embeddings.
Word embeddings.
Yes.
I've heard that term before.
Word embeddings are basically just vectors that represent words.
Okay, so each word gets its own vector
Right.
and the vectors. capture the meaning of the words?
Exactly.
Okay, so we've got word embeddings. Now what?
Once we have word embeddings, we can use them for language modeling.
What is language model?
Language modeling is the task of predicting the next word in a sequence
Yeah.
based on the preceding context.
So it's like those AI writing assistants
Mm.
that can predict what words you're going to type next.
Exactly.
Okay. And how do we train these language models?
We typically use a sliding window approach
Yeah.
where the network learns to predict the next word based on a fixed size context window of preceding words.
So it's like the network is looking at a few words at a time.
Right.
And trying to predict
Yeah.
what comes next.
Exactly.
Okay. And once we've trained
Yeah.
a language model,
Mm.
how do we actually generate text?
There are different decoding strategies that we can use. One common strategy is greedy decoding, where we just pick the most likely word at each step.
Okay.
But that can sometimes lead to repetitive or predictable text.
Right.
So there are other strategies like beam search and sampling-based decoding that can produce more diverse and interesting text.
Okay, so we've got all these different ways of generating text. And this chapter also explores more advanced models like LSTMs and CNNs.
Right. LSTMs and CNNs can be used for text generation as well as for image processing.
Okay, I thought LSTMs and CNNs were mainly for images and sequential data.
They are,
Okay.
but they can also be adapted for text processing.
So it's like using a tool for a different purpose than it was originally intended for.
Exactly.
Okay, so we got all these different models for text generation. But I'm curious, what comes next? Is there something even more powerful than LSTMs and CNNs?
There is, and that brings us to Chapter 10, NLP 2.0, using transformers to generate text.
All right, transformers.
Transformers are the next evolution in natural language processing, and they've been making waves in the AI community.
I've heard about transformers. I know they're behind some of the most advanced language models,
Right.
like BERT and GPT-3.
Right.
So what makes them so special?
Transformers address some of the limitations of traditional RNN-based language models. In particular, they're able to handle long-range dependencies in text.